Afternoon, everyone. Greg will now present on the MWA data archive and systems update. Without further ado.
Thanks very much for that. Can people online just let us know if you can hear us and see my slides?
Yes.
Yes, excellent. Thank you very much. I'll do it like this. So hello, my name is Greg Slick and I'm the MWA data manager. I'm going to take you through a bit of an update on the MWA archive and some of the systems stuff that me and my team are responsible for, and as well as okay, cool. As well as a few other topics, for example, the just an overview of the MWA data flow, which we've already seen today anyway, but I'll just point out a few key things. The MWA data retention policy and the implementation of that. A refresher for some, but new information for others would be the MWA data collections, MWA calibration pipeline update, as well as things happening at Palsy and work still ongoing on the MWAX correlator and related systems. And then just a bit of info on scaling up and future work that we're doing. So this is my team. So this is the CARA, so the Curtin Institute of Radio Astronomy Software and Systems team. So we have a Venn diagram that I guess massively overlaps with what you would consider to be the MWA operations team. The majority. Oh, that's better. So the majority of activities that my team undertake are MWA related, but not exclusively. And as you can see, we've got a few new faces as well. And I think it's really important when we're at these meetings to introduce the teams and the people that are behind a lot of the work that goes on behind the scenes that may not be necessarily visible. So I'll just introduce a few, all of the team, but especially the people that are here today, which will mean that you'll be able to go up and say hi. So we've got Maureen Rajendran. You've already seen Maureen's talk this morning on MWA ASVO. We've also got over there, we've got Dev Null, who also gave the workshop and knows so many things about many things. And we've got, so myself, I'm here. So the other people in my team are Chitru Shrestha, so another sort of full stack developer, so working on web stuff, ASVO, the MWA website. Andrew Williams, ex-optical astronomer, so we turned him from the dark side into radio astronomy. If you've been involved with the MWA for any amount of time, you probably already know of Andrew Williams at least, because he's been a part of the project for a very long time. He handles all of the telescope scheduling, monitor and control, tons of stuff. And we have two new faces in the team. So Christopher Phillips started with us in January this year and is a software engineer specializing in optimization and low-level code. So Christopher at the moment is getting to grips with the MWAX correlator code and a lot of the low-level systems that deal with the data coming out of receivers. And we've just recently hired Jamie Pierce, who is our system administration lead. Previously, the system admin tasks have been separated out into or spread across multiple people. So Jamie is now a dedicated resource for that. Specializes in cybersecurity and system architecture, and will give us, I guess, a good footing in those areas where as time has gone on, cybersecurity and resilience and protecting our systems from cyber attacks, etc., become really important, especially because we've got various websites and web services that are all publicly facing. And looking at the logs, you can see that they are always constantly under attack. So it's good to have Jamie on board for that. So this is the MWA data flow. You've probably seen this diagram before. It's probably just important to point out that from my point of view, with the archive and systems, a lot of our efforts go into that top blue box on the right-hand side, where we've got the media converters and the correlator, the online archive. We transmit all of the data as soon as we can off to the data cache at Curtin University, which is the very far right-hand block there. So we have 2.5 petabytes of storage there, and the main purpose of that is to get the data off the correlator boxes as fast as possible. They've only got limited storage. So that way, if there's any issue in getting the data to its final destination, which is down at the Pawsey Supercomputer Centre in the bottom left-hand corner of the diagram, basically means we can buffer up 2.5 petabytes worth of data before having to stop operations on the telescope. So that's really important because there's often regular maintenance and other issues that can sometimes cause Pawsey to not be available for ingest. And we recently had a situation where Pawsey had an unplanned outage for several weeks, and it was no sweat at all because we had this data cache available, and we just buffered up the data. And once Pawsey was back online, we opened the floodgates and it all flowed through, and the telescope didn't miss a beat. So the investment in that data cache has already paid for itself. The other aspect here, I guess that's worth noting, is with the MWA being the MWA archive being a raw data archive, it really is up to the science teams to produce the science products and then publish those science products. And so it puts a lot of burden on researchers, but it is one of those things where we draw the line between where operations finishes and science begins, pretty much at the point where you download the data from MWA ASVO. So this is what the archive looks like as of a few days ago. So 54.2 petabytes. We have 3.2 petabytes remaining, which is only 6%. You can see that the majority of data is stored in the Banksia system. So that's the tape system. Pawsey have 2 robotic libraries that operate redundantly to store and retrieve data with several different tape drives at their disposal. So what that means is when you do request data through the ASVO and it happens to be on Banksia, which based on that pie chart, it's most likely to be on Banksia, especially if it's older data, you basically have to wait for the Pawsey system to stage that data off the tape. The staging times can vary from almost instantaneously, if you're lucky, all the way up to sort of half an hour or sometimes even more. But it's actually not too bad. It's been pretty consistent for quite some time. So we've got 750,000 observations with data in the archive across 167 different project proposals. So this is the growth of the archive over time. This diagram takes into account any data that has been deleted. So this is sort of the net archive we have at the moment. And as you can see, there's pretty consistent growth across time. There's various features to this graph that you can sort of pinpoint as to things that happen. So for example, at the end of 2017 is when MWA phase 2 began taking observations, and so there's quite a bit of a jump up there. And the next slide here shows what the ingest into the archive is if we hadn't deleted any data. So we've taken in 68.3 petabytes since we began science operations in 2013, which is actually a pretty staggering number for our little project. So this chart is just showing, probably very hard to see actually, I apologise, just the volume of data by project. I think probably the most important feature here is not to name and shame different projects with different amount of volumes of data being used. It's very more to point out that the bottom pie chart there of other is getting bigger and bigger every time I make this plot. So which goes to show that there are a lot of smallish projects that are filling up the archive, and we no longer have this idea that there are a couple of gargantuan ones and then a lot of small ones. We actually have a lot of small to medium ones. So over the last 6 months, we've ingested just under 2 petabytes, which is a nice leisurely amount, and probably not anything exciting to say about that. I looked at the volume of data we've got and categorized it by visibilities versus voltages. And you can see we're at about 2/3, 1/3 at the moment. Obviously, the voltages, which is the data coming straight from receivers, takes up a lot more space, but is essential for pulsar searches and other things. And visibilities taking up 2/3 makes a lot of sense. Most of the observations are visibility observations, and the different labels on this chart are just the different modes of the telescope, and that will tell you whether it's MWAX or whether it's legacy stuff. But this is what I wanted to show you, especially this plot I made, is you've got year on the x-axis, so that's the year of the observation. And then the bar, so the y-axis, is the number of downloads that we've recorded against those observations. The download data is extracted from logs over 10 years, and unfortunately the data is not 100% complete. It's pretty good, and the data from 2018 onwards is 100% complete because we had a different way of storing the download information. So basically database versus logs. But the interesting thing here is to see that the most downloaded data is the oldest data. And now that might not be that surprising, considering that the oldest data has been in the archive for the longest, so therefore it would have more downloads. But also you have some key projects that their data was taken around that time. So you've got the early EOR seasons, you've got the early Gleam seasons as well. And so it's probably no shock that that's the case, but it is interesting to see that we do have quite a few valleys of very few downloads. And I think this harkens back to what Stephen was talking about, where the MWA archive is an untapped treasure trove of potential discoveries. And I think over time, hopefully with help from all the collaborators here, especially our new Swiss friends, we can actually get more downloads in these valleys and have novel looks at this data. So just from an MWA ASVO point of view, this is just showing the split of what people request. So the biggest pie chart there is CASA measurement sets. So people request data to be converted into CASA measurement sets. The next biggest is UV fits, and then 22% of the downloads of data are the raw visibility files. So that would probably be people like Dev doing EOR stuff. So that way all of the processing is under their control. But I just thought it was interesting just to see that comparison. This will probably get prize for the worst slide in the entire project meeting. So Stephen, I will gladly accept the prize from you after my talk. So on the right-hand side, we're looking at the number of downloads and the amount of downloads in terabytes. So since 2017, or since the end of 2017, we've served out just under 24 petabytes of data to users, which I think is a pretty impressive number. And that's 500,000 download jobs, where each job is a single OBS ID. Also, the top right chart just shows a nice increase in the number of users that we've had on the portal. And I ran a little statistics here in the bottom right, which is our MWA ASVO Olympics. And so we've got the bronze medal going to Theodora. We've got the silver medal going to Stefan and gold medal going to Dev by a mile. So thanks, Dev, for your patronage. So just an update about the data retention. So with the archive being squeezed at the moment down to 6%, we are in a position where we need to balance the fact that we want to keep as much data as possible with the glaring reality that we don't have infinite space, along with the other complication that we want to store the data in as raw format as possible in order to make it as flexible as possible and make it available for novel uses. So these are all in conflict with each other, and unfortunately, at the moment, the solution we have is to basically enact the data retention policy, where we basically try to remove the oldest, worst, or least value data that we can find in the archive. So Stefan and Chris Risley and myself, we had identified some low-hanging fruit in the most recent cycle. So that was back in October 2023. We did a small test run of a petabyte. The list of what we had proposed to delete went to all of the members of the MWA collaboration by email with links to basically see the exact ops IDs and see a summary. MWA members had 4 weeks in which to review that list and then to come back with any concerns. And we didn't have any concerns that time, and it's probably not surprising because we were able to find lots of very poor old observations. And so it wasn't any surprise that that was okay. But in the next round to come, which will probably coincide with the TAP coming back with the list of proposals that are accepted for the 2024 B semester, we will run another round of deletion, and Stefan and Chris and I have already identified some good choices for that, which we also don't expect any issues from. But over time, this may change. Yeah, and just to reiterate as well, if you have an issue with any of that data, you'll have 4 weeks, and you basically apply to Stephen to say why you actually want to retain the data, and what you're going to do with it, and by when. So, right, okay, in that case, I'm going to skip this slide because I've taken too long. We have collections. Go to that URL and have a look at them. That's data that's ring-fenced, that can't be deleted because we got a very generous grant from ARDC and worked with Pawsey and AL to give us extra storage to make sure that those data sets don't get touched by any deletion. So there's a whole bunch of changes coming through from Pawsey, which have required a lot of effort from my team and others as well. I won't go into all those details, but it's basically the Garawala supercomputer coming to end of life at the end of December, or sometime in December, and a migration to the Cetonix supercomputer, where MWA ASVO needs to migrate. Also, a lot of our software needs to be modified because the Cetonix supercomputer does not have any NVIDIA GPU nodes. It's all AMD. And whereas traditionally most MWA software is all based on CUDA. So there's MWAX work going on. So even though the MWAX correlator and associated systems are effectively feature complete, there's still work going on because there's always things to do. So we're looking at optimizing the correlator reordering code. In our simulations at 256T, the reordering of the data was taking 40% of the runtime. So we've got Christopher on that job. He loves optimization, so he's working on that now. There's some refactors, some other stuff going on. Probably an important one as we get more and more receivers and therefore more and more tiles is that we're working on better packet loss reporting. So using multicast UDP, you can effectively get packet loss due to various reasons. Nominally, it's always extremely low, but as we increase the number of tiles, we're going to be increasing the network traffic, and we want to make sure that we have good monitoring of that to make sure that the packet loss does not grow as we increase the number of tiles. So there's also work going on the Kelvin calibration pipeline. So this is work that builds on Marchin's calibration pipeline that he built for the MWA ASVO. So this is when you tick the box in ASVO that says calibrate my data. This pipeline is intended to handle that situation, and that's what Marchin's has done. We've built on top of that, and we're using Hyperdrive to do the calibration. And we're also making it so that any new calibrator observations that come off the telescope will automatically go through the pipeline in order to get the calibration solutions generated. So this sort of gives us this near real-time calibration solution, as well as the sort of offline mode where ASVO users will request a calibration solution if it doesn't already exist. So scaling up, so this is a really important one, as you'll see in the next couple of talks about new receivers for the MWA and adding more tiles. So this plot on the right is basically showing that as the number of tiles goes up, obviously the number of visibilities scale with number of tiles squared. So you get to see this quite an enormous data rate increase. So when you're down at the 40 kilohertz 2-second averaging out of the correlator, the curve isn't actually too scary, although it's still obviously 4 times more data than at 128 tiles versus 256T. But if you're at the data rates that we used to have to be at for the long baseline configuration, which is 10 kilohertz averaging at 0.5 seconds, that curve gets awfully scary awfully quick, meaning bigger data sets, and everything becomes a bit harder. And just for comparison, I've put the yellow line there, which is what a VCS growth in data looks like when we get to 256T. So yeah, you're effectively looking at 30 gigabytes a second for VCS observations at 256 tiles. So what does this mean? So the MWA's hardware has been set for 256 tiles. We haven't run it at 256 mode, the whole system, but we have tested components with 256 tiles and we're fine. So we're going to see how that goes as we scale up. Some modes won't be available as the number of tiles increase. So the really super high resolution modes. The 100 gig link will start to actually become a bottleneck. Obviously there's pressure on archive capacity, so we'll need to handle that with identifying low quality data for deletion and more frequent, larger deletion of older, less value data. Obviously, compression is another thing as well that hasn't probably had the resources thrown at it to really get traction, and that's something that I'm hoping that we can actually do with the collaboration and work on that. And obviously bigger storage and compute requirements. And of course, the fringe stopping feature that was introduced last year is going to be crucial to all of this scaling up, because you can use much more aggressive averaging as you get up to a large number of tiles. So future work, I'll really quickly just say that another thing to beat this data deluge that we're going to be coming into is work on a coherent beamformer for MWACs. So this would actually be just part of the system. It's in very early stages, and we're just basically looking at a design and gathering the requirements. But basically, this could replace many of the huge VCS observations with much smaller beamformed products, depending on how many beams you pick, etc. Yeah, it needs to integrate obviously with the existing ecosystem of the monitoring control and MWA archive and ASVO. And that's just a thank you to lots of the partners that without which we would not have MWA. Thank you for listening.
you have any questions for Greg?
Yeah, sorry, I missed a bit, but what are the plans for scaling up the storage, right? Today you're 68 petabytes, talking about scaling the storage. So how is it going to grow? Double X or?
Yes, so the question was how we're going to scale up our storage. The answer to that is we can't. So the storage is provided to us by Pawsey as part of our partnership with Pawsey. So if Pawsey were to bequeath us with more storage, then we get more storage. That's not likely to happen anytime soon. So we are definitely looking at a squeeze because we obviously have finite capacity, and basically we would have to get funding to basically boost that storage. It doesn't look like there's any sort of saviour from Pawsey on the horizon. But the handy thing is that in the same way that the ARDC collections added several petabytes from external funding, Pawsey are very open to, if we provide the funding, they'll add the storage. So so there is that. So they've the Acacia system that they've got is Ceph. It's highly modular, highly scalable, and basically means that yes, money is the only thing holding that back. Yes, Miguel.
Somewhat related, because of the volumes going up. Is there a discussion with ops team how they serve to a baseline bounce? So, for example, for people who are survey, people in 256, certain people surveys might want to set tenants because those are useful to them. EOR, where it's an EOR observation of the same data field again, so nobody wants to use that for a survey, and the log baselines are already sort of thing. So a lot of those cases you get on order to in data volume.
Yes, absolutely. So the question was
Without actually throwing it away.
yes. So the question from Miguel was, have we considered providing options for people to, say, drop tiles or baselines from the observations to make them smaller if they don't need those baselines? The answer to that is that yes. So it is something we can do. We can do it at the receiver level. So we can basically turn off the receipt of data from an entire receiver. We can do that on a per observation basis, but at the moment it's a bit of a manual change. However, that would not be something that's impossible to automate more, so that we could have it on a, maybe in a single night, we're doing Miguel's observation, so we turn off receivers 15, 16 and 17, which are the hexes or whatever, and then turn them back on again for the users that are having later observations that do want those baselines. So I think it's just about automating that to make it.
Well, let me ask you another question, though, particularly for the baseline ones, because you could imagine something where you're not bucking but you have essentially a job in the background or transmit to Pawsey, which just simply does downside. So you write the file, but you then end up saying, hey, compression file needs to drop these baselines. So.
Right. So Miguel was just suggesting that you could do a post correlation downsize. That is possible, but I think it's easier just to sort of turn off that data in the first place, I think, rather than try to excise it later, because you'd need some computing power to do that and time, and we generally try to get the data out of the correlator and off into Pawsey as soon as possible. This would probably slow that process down maybe and create a bottleneck in itself, but yes, I mean, I guess we should be looking at all these options and see which is feasible, but it seems to me the M&C option is much easier to get done quicker, although Andrew Williams may disagree. Sorry, Andrew. Yes.
Just a quick question. Visibility data are all compressed now. Is it correct? Or Oh, and the other part of it is that VCS data, I think, are not compressed. Would you gain anything by compressing those? Would it be possible to do some more compression in the archive?
Right. So Martin's question is just about compression and which data is compressed and which isn't, and the difficulty of visibilities versus VCS data being compressed. Prior to MWA's correlator, and after changes that Steve Ord made to the legacy correlator, so this is probably, I think, between October 2014 and 2021 when we installed MWA's, the visibilities are compressed out of the correlator because the visibilities are stored as integers and they losslessly compress very nicely. The MWA's correlator produces floating points, so 32-bit floats, which have obviously much more difficulty in compressing. We can compress them. We get about 5% smaller with any of the compression algorithms we try, but it takes about 50 times the real time. So a 1 minute observation, will take 50 minutes to compress. So it's not really worth the effort. So I think any future compression strategy that we do, first of all, needs to be something that the entire collaboration can agree on, or maybe there's different compression for different science cases or something, but it will probably end up being lossy compression because there's no other way to really handle that. The VCS data, we have tried various compression algorithms. It does compress better than the visibilities, but obviously the huge files make it quite a computational issue, and we just don't have that level of computation between the correlator and Pawsey. So the data cache servers are storage servers. They've got very, very poor compute capability, unfortunately. So it's definitely something that needs more effort to look into all the options. Yeah.
A quick one, if you don't mind. I know that I keep asking this, but I mean, you mentioned that obviously VFormer is the way to work around the data. Yes, particularly the number of tiles. So based on where things are at the moment, like file and what's an indicative timeline?
No idea at this point. So we need to gather all the requirements first to see what it is we're building, what features it needs to have, what could a minimum viable product look like. Because as we've been going through the design and requirements, there's a lot of open questions. And we also need to figure out exactly how much the hardware that we've got with the MWA service, what it can do. Like, can it correlate and beamform at the same time with n number of beams? This is all good questions. We need to be spending more time on this. So sorry.
No, I mean, it looks like it's the options that we consider is like correlation and beamforming simultaneously. But what is correlation or beamforming? That's one possibility.
Yeah, sure. And I think in a minimum viable product, I think we would go that route in the first instance and then see how that forms on the hardware that we've got. And then, of course, as the number of tiles scales as well, what's it going to look like at 256T versus now? It could be very different.
Thank you again, Greg. Our next speaker is Yajin Wu, who is going to tell us about the status of the SHAO MWA PH3 receiver.
So, hello, I'm Yang Wu from Shanghai. Shanghai Astronomical Observatory. So I will introduce the design process of the SAW MWA Phase 3 receiver.
Yeah, so.
So first I will introduce the background. Our observatory take part in the project from the MWA Phase 2, and at the stage of Phase 3, we will supply 16 receivers of the contribution. So by ourselves, this project is funded by the SK pre-study project. And now, I think as we know, now the MWA has 255 tiles, and only half of them are working on Phase 2. So we need another 16 receivers for the 128 times. This is the Phase 3 upgrade plan. So for the receiver requirements, we need more sensitivities by using more ADC bits. So, and also we want to use the oversampled PFD to replace the critical to get a more useful bandwidth. And also we need the standard network packet to use the standard equipment. Also, we need a new function of raw voltage capture, and also the flat spectral response. And this is the signal bus. The component in red is the contribution by us. And we designed this receiver by I think maybe we divided it for layers of the design. The basic is the hardware, and we developed the function models on hardware, and then the OS system and the driver, and then the MNC software. So the specifications are like this. 16 RF input, and we have an SC module, a very large range of the gains for the RF OF and the cable transmission, the PFD module, and the output is 24 channels of each antenna of each tiles, and use this the UDP packet, and also we have a beam buffer function for the more voltage for 1 second. And this is the hardware. At the top of this is the analog amplifier, and the bottom is the ADC and the PCA board. And the function module, the PFD is compatible with Phase 2 mode, and the frequency of response is not flat between two channels, and this is the new model of phase 3. So we have a conversion of this. We use the example to make the frequency overlap between two channels, and the cause is we have the higher data rate, and this is the new function of phase 3. We need to capture the raw date and cache it, and then transfer to the Ethernet when triggered, and the data rate is about 84 Gbps of each receiver, and this is the function, the structure of this function mode. And also we designed a software or web server for the MWA, and this software can be accessed by IE browser or Client, and this is the GUI of it. It shows the status of this receiver, and also the histogram of each RF input and the spectrum, and the EMI is very important for this, and we measure the EMI of the components, and then design the shielding box, and this is the result of the ADC and the FFC board, and then we designed the box, and then integrated them together and designed the shielded rack and the airflow to get the EMI according to the EMI standard. And after we finished the prototype, we constructed this platform for a remote test, and the tests are done by Tikios. He log in a remote and test all the functions. And this is the result of this test: the gain of SC and the analog shape and the PLD shape and the correlation and the integrated spectrum, and also tested the new function of the low voltage capture, and the result is shown in the middle of this, and this can capture the change of the input. And this is the EMI test occurring, and the result shows is very good, I think. And this is the schedule of the receiver, and we have shipped the prototype to Curtin at December 32, and I have a mistake here, and the prototype installed at MWA at April 2024. I have a mistake here, and for the other 15 receivers, they were cutting at at July this year. And we use this hardware, and we have some other application work about for the backend and for single dish observations, and we use the baseband data and using the DSPSR software running on CPU to do the coherent dispersion, and we have some observations. And also we want to use this backend for the array, and we want to put several antennas together to get a larger signal to noise ratio. And this is the result of the early stage. And that's all. Thank you. Thanks to MWA teams. Thank you all.
Any questions for you?
I'm so excited about this. What has been most challenging part getting this going? More fun.
At the very early stage, I am a little worried about the EMI, and when designing the functional modules, the very difficult part is the synchronization of the UDP payload between channels, and we have failed many times. Thank you.
Any more questions? If not, we can move on to our last speaker of the day. So we have Jake Jones giving us an update on the MWA receiver project.
Okay. Hello, everyone. I'm Jake Jones. I work on the engineering, MWA engineering and operations team. Today, I'll be giving you an update on our progress and upcoming work on the new receiver upgrade project. Yeah. So our current set of receivers, the RRI receivers, look a bit like this. They take 8 tiles each. And we have 16 of them currently, as we all know, and so we can only have digitized 128 tiles at a time. And so it consists of a bunch of digital hardware, the digital receiver, aggregator, power supply, ASC, and that's all situated inside of an EMC type box and sits on a pad or a weather enclosure. Now these are almost more than 10 years old now, and they've served us very well, but they do have some shortfalls. They have 8-bit ADCs, which can saturate if you have RFI or any sort of burst. They only have 5-bit output precision. And of course, the critically sampled PFB as causes these spectral effects at the channel edges due to aliasing. Of course, they're just getting old and a bit annoying to deal with. So that leads us to phase 3 that we covered. We got a new correlator, that's great. But in order to achieve 56 tiles concurrent and oversampling mode, we need new receivers. So the core requirements of a phase 3 receiver is to have at least a 12-bit ADC to increase our dynamic range, 8-bit output precision, and it should support 2 modes, the compatibility mode and the oversample. And of course, this oversample mode is meant to fix this problem with the aliasing packaging. And we want it to also support standard POPs hardware and networking. So we actually already have 2 phase 3 capable receivers already. It's the National Instruments based receiver, or NI receiver for short. They have 12-bit ADCs, they support both modes, and they've been in service since about the end of 2022, I think. And they're both currently connected to the F and G group solar panel tiles. And they've been operating, like I said, for a while now, and they seem to be going well. But yeah, of course, we only have 2 of them, and we're not getting any more in the future. So, which leads us to the new shower receivers. At this point, I want to thank the Shanghai Astronomical Observatory and team there. They've done a great job developing the new receiver. It's fully phase 3 capable, 12-bit ADCs, supports both modes, 10 gig networking, it's got built-in ASC, it's got all. It's great. And so in April this year, we deployed the first prototype. We installed it inside the field container, which is an EMC type container. You can see it there, rack mounted. It's hooked up to some of the G group tiles. It was also deployed alongside the NI receipts. So here we can see the very first PVDs we got, power spectral density across the whole band. In the red box are the PVDs from the shower. And so the main purpose of this deployment was to validate the functionality of the receiver and to integrate it within the telescope. So that's integrating it with the MFC system and with the correlator. So here's some of the initial results. We took a VCS observation of some calibrator source. I computed the autocorrelation of 3 adjacent pulse channels, and you can see the typical PFB response of the critically sampled PFB. The different colors represent the different receiver types. So we're operating in compatibility mode at the moment, and the point to be made is that all of the receiver types look the same. So moving on, so if we compute the correlation between some tiles of different receiver types versus a reference tile, the shower receiver is in red, NI in blue, and the RI in black. This is just a single course channel. And as you can see, where you can see the aliasing happening at the edges of the channel, just causing these non-linear effects in space. But otherwise, the shower receiver incompatibility mode is emulating exactly the other kinds of receivers. We ran a MWAX correlated job and it all worked fine. This is what we call a fringe plot. We use it all the time to diagnose issues with the telescope. It's just a phase versus frequency for different various combinations of tiles. Everything in the red box involves the shower receiver. And so this is just confirmation that it works and is fully integrated with the MWAX correlator. Then we switched over to oversampling mode, which is the exciting part, I think. We did the same thing, took a VCS capture, computed the order correlation, and so I plotted the overlapping coarse channels, and you can see the shape of the filter, and you can see that it starts rolling off in the overlapping regions that get thrown away anyway. In this figure, obviously, there's no near ripple applied. This is the phase. Obviously, we only have the NI receiver and the shower receiver. So the red is a shower receiver tile correlated with an NI receiver tile. Blue is NI versus NI. And also, I've discarded the oversampled redundant regions. So we're just in the pass band, and the phase is flat across the whole band. So that's exactly what we're looking for from this. And again, we exercised the oversampling mode with the MWA correlator, and it all went smoothly. This is just a correlation matrix of all the tiles involved, and the shower receiver was on G tiles, which is in the bottom corner, NI receiver, the F tiles. So that turned out great. So after the deployment, we got a delivery of 16 new shower receivers, and we were very excited, as you can see. And so, but of course, now we have 16 shower receivers, we need somewhere to put it. And so our mechanical engineer, Luke, has been working hard developing a new receiver field cabinet, as Stephen already showed some photos of. These are some renders. It consists of a weather enclosure and an EMC cabinet, type cabinet situated within it. So the weather enclosure is, the main purpose is to shield it from the sun and rain, and we designed it in order for it to be easily serviced. So open doors, using gas struts so that they open, and yeah. The field cabinet, of course, is an EMC shielded cabinet. All of the doors have EMC gaskets. It has an 1500 kilowatt air conditioner. It's a standard server rack, so you can fit any server rack equipment within it. And it's designed to store 2 shower receivers per cabinet. So each cabinet will support 16 tiles, not 8. Like these that you've already seen these photos. We've assembled it in the lab. Well, so this is sort of the internals of the cabinet. Like I said, it contains 2 shower receivers. We've also developed some beamformer controllers, which supply power to the beamformers and can also send pointing commands. Each cabinet needs to have a 40 gig data switch, which aggregates the data from 2 receivers and puts it on a 40 gig link. We have a timing module that receives the clock and the PPS from the main correlator building and distributes it to each of the receivers, and air conditioner and a control unit that can read sensor values, temperatures, control the air conditioner, etc. And so, yeah, we assembled the full system in the lab, and we've powered it on and set everything running, and everything has gone smoothly so far. We operated the air conditioner under full load, an ambient temperature of 30 degrees, and it's all gone very smoothly. And so currently we are working on electromagnetic compliance testing. And yeah, so we're in progress there, making sure that it's as low as possible. And so the plan is in about a month or so, we'll deploy the first prototype cabinet. So 2 shower receivers in a cabinet on a pad. And so we'll use that as a test bed to test the system and learn from it. we currently have the next 8 in production. We are targeting to have deployed all 8 cabinets by mid next year. So yeah, in summary, we've validated the shower receiver by deploying it to site and integrating it within the telescope, designed and fabricated. We are fabricating 8 new receiver field cabinets to support an extra 128 tiles. And yeah, so, and yeah, like I said, we're deploying the first cabinet very soon. And of course, thanks again to Xiao for developing the receivers. And I also want to thank the engineering and operations team. They've been working very busily to get this all done and deployed as soon as possible. Thank you.
Any questions for Jake?
Yes.
So one thing is just kind of get to the back of my mind, clock distributions. Is that essentially a replica of the one, or is it a different clock distribution system? It's not sexy.
Yes, it's a different system. It's based on the White Rabbit system. And so it distributes the clock over fiber, and the White Rabbit system will account for the fiber length. So it doesn't matter if the fiber lengths are different. All of the PPS will reach each receiver at the same time.
Has that been?
We've been using that system on the NI receivers for the last few years, and we've, it's working so far.
It might be just as a little tag to the side. Strong suspicion says user error.
Yeah, we had some initial issues with the control interface, and we learned that if you are constantly trying to ping it, it sort of reboots every now and then. You shouldn't do that. So you just let it, we don't constantly ping the MWA interface on. Yes?
Question.
Yeah, thanks. So I noticed that these new cabinets seem to be quite a lot bigger than the first ones. And you show 2 of these devices inside the cabinet. Is there a reason for that? Are you expecting to be able to put more of these devices inside the cabinets, or is there a need to have that air volume for other design reasons?
It was initially designed to also support 2 NI receivers, which take up a lot more rack space.
Okay, yeah, they're the bigger ones you showed, yeah.
Yeah, so that's one.
Oh, you don't need to do that, do
No.
You want to retain the flexibility to do it if we need to.
Okay.
Yes.
It's good to be agnostic to the absolute specifics of a particular receiver.
Sure, yeah.
Any more questions? If not, let's thank our speaker once more.